The Big Bang. Out of nothingness, a universe is created which will forever capture our imagination. Stars are born, stars die. Galaxies spiral into existence. Solar systems are assembled. The incredible forces that shaped our universe on Unraveling the Cosmos. $13.8 billion years ago, this was our universe. A point in time and space known as a singularity. Smaller than an atom, and packed inside it all the mass and energy that was and ever would be. One scientist described it simply as potential. Then, for reasons we may never know, potential is realized. The event, the Big Bang, occurs with unimaginable force. Nothingness is replaced with blinding, swirling energy. This is the universe, just 1/billionth of a second after its birth. Here, deep inside the Big Bang, all the way down to the molecular level, there is a searing cauldron of radiation. A soup of nuclear matter, so hot that as atoms and other building blocks of matter try to form, they are quickly blown apart. Now, just a microsecond after the Big Bang, if we could view the expanding universe from a vantage point light years away, we'd observe in these blue ripples the entirety of space forming, rippling outward from the Big Bang in waves of energy. Within a millionth of a second, the universe is the size of our solar system and as dense as the core of the sun. It's doubling in size, all within a blink of an eye. Its outer border is creating space as it goes, because just beyond these ripples of matter, there is no space. The outer edges are bending and folding as the universe expands. Scientists don't all agree on what the universe is actually expanding into. Out here, time and space itself do not exist. So we are depicting the undepictable. But if we could see this expansion just moments after the Big Bang, this is one theory of what it might look like. This is the chaotic creation of space and time itself. At the edges, we are looking at the fabric of our universe, finding its way from nothingness to everything. And while space and time are being created at the edges, back down here at the molecular level, we would observe a sea of particles as temperatures begin to drop to about 1 billion degrees. If we were to examine more closely, we could see the nuclei of hydrogen and helium. The universe is cooling just enough for atoms to form, and they do. Trying to see the universe at this stage is impossible. As the minutes turn to hours, the hours to years, and years to centuries, the universe is still a hot mass of plasma and radiation. But the process of cooling continued. And as it cooled and expanded over hundreds of thousands of years, it became less dense, like rocks breaking apart. This era, before the birth of stars and galaxies, lasted for millions of years. Before we see how stars were born and space became a brighter place, let's take a look at how our universe actually expands. In all the dramatic evolution of the universe, the one constant has been its continual expansion. Imagine a three-dimensional balloon slowly inflating. As the balloon expands, the stars and galaxies move further apart, away from the Big Bang at the center. The size of space grows larger, but the stars and galaxies remain the same size. The universe we know is still expanding, and although there was nothing that could match the power of the Big Bang, there are still forces in the universe that simply defy our imagination and are every bit as wondrous as the beginning of time and space. For millions and millions of years after the Big Bang, there were still no stars in the universe. But the universe was rehearsing ways to make them. The seeds of these early stars were planted in immense hydrogen clouds that became so dense they ignited nuclear hydrogen bomb-like explosions. Luminous, short-lived behemoths were born, 100 times larger than our sun, 1,000,000 times brighter. And even though these very first protostars would burn for a very short time, about 1,000,000 years, the universe was forever changed. The cosmic dark ages were over. Everything we can see or touch today was born from these early stars. This is how our own solar system began to form 4.6 billion years ago. From the wreckage of a supernova, interstellar gas and dust began to cluster together in a molecular cloud known as the solar nebula. As this cloud collapsed, its center became a hot, swirling nuclear fire. Our sun was born. Looking at our solar system, more than 4 billion years ago, strong stellar winds expelled gas, dust, and debris from this new star. Clumps of molecular matter formed and orbited around it. These were the seeds for planet formation, the blueprints for Earth and our other planets. And as they filled the early solar system, they coalesced into larger and larger formations until they became boulders so big they eventually had their own gravitational fields. These inner rocky terrestrial bodies were all orbiting at roughly the same speed around the sun, making it easier for them to coalesce. This process is called accretion, and it's how our solar system began to take shape. Not all bodies found a place in orbit around the sun. Some icy rocks were flung out of orbit and became comets, destined to wander the reaches of the solar system. But after 2 million years circling around our sun, the larger bodies eventually became early planets, and they began to claim their own space. Coming together in a protoplanetary disk in a violent corner of space. Once these early planets became large enough, gravity and pressure shaped them into spheres. This shape is a constant in our universe, from planets and stars. to molecules and cells too small for the eye to see. They all perform a similar cosmic dance. Whether it's electrons orbiting a nucleus, our moon orbiting the Earth more than 200,000 miles away, or neighboring and distant planets orbiting the Sun. They all perform the dance of the spheres. After a fiery and cataclysmic start, our solar system today, around 4.6 billion years old, has reached an equilibrium. A perfect harmony of the spheres around our sun. But over time, nothing in space remains constant. "200 million years after the Big Bang, the universe looked a lot different than it does today. There were no galaxies yet, or planets. Just clouds of gas and some early unstable stars called protostars. Massive bodies of heat just burning through their hydrogen. And when that hydrogen was gone, they collapsed. Behold the birth of a supernova. Its light capable of outshining an entire galaxy. These supernova blasts did more than light up the universe. They also sent elements like carbon and oxygen, which had never existed before, into surrounding gas clouds, changing their chemistry. Inside these clouds, carbon and oxygen began to burn, causing massive chemical reactions. From all the chaos, a second generation of stars was created. Stars that looked and behaved more like our own sun. They often collected in dwarf galaxies. This dense ball of dust and gas is a dwarf galaxy known as a starburst, one of the oldest in the universe. But how did galaxies form? Galaxies like our own Milky Way. As large as galaxies are, it's the forces at the center that drive them. No stars live forever, but some are reincarnated, leaving a neutron star in its wake. Surrounding many neutron stars are disks of debris, like those around Saturn. These extremely dense stars are small, just 12 miles in diameter, smaller than New York City. Yet they have a great deal more mass than our sun. Their enormous gravitational fields actually bend light as it passes. Some neutron stars have gravity that's 100 billion times stronger than what we experience on Earth. How do you explain the force of that kind of gravity? Imagine it this way. Matter is packed so tight on a neutron star that a sugar cube of material, if you could find a spoon strong enough to hold it, would weigh the same as Mount Everest, about 1 billion pounds. Think about that. On a neutron star, the crush of gravity is so strong, it would be like condensing the highest mountain on Earth down to a spoonful of sugar. Some neutron stars have magnetic and rotational axes that are misaligned, and they spin wildly in space with brilliant beams of light sweeping the skies around them. It wasn't until 1967 when scientists observed a flashing star in distant space. They were seeing the beams of a special kind of neutron star called a pulsar. The recently discovered Black Widow pulsar earned its nickname by sucking the life out of a companion star that orbits around it every 93 minutes. Mass from that companion star is being absorbed by the tremendous magnetic field of the pulsar. It spins at nearly 400 times per second, emitting a pulsing beam of light. Sadly for the companion star, this breathtaking dance will also be brief. In just 100 million years, the Black Widow will eventually devour its mate. There are so many forces in the universe, some beautiful and some unimaginably powerful and violent, as we'll see when we come back. A pebble with a nearly insignificant mass. But what if it struck with just enough force to knock an asteroid ever so slightly off its trajectory? These are the kind of random, unpredictable collisions, 1,000,000 to 1 odds, that happened millions of times billions of years ago when our solar system began to form. A chance collision, changing the path of an object so slightly that 1,000 years later, it finds itself heading straight for a random early planet. Collisions like these help shape how every solar system in every galaxy would eventually form. A new debris field is born, and a planet gets a new crater. Gravity will pull most of the debris back in, but some of it will escape and go on to become yet another clump of travelers looking for their next encounter. $4.5 billion years ago, one of those travelers brought us a collision for the ages. Scientists call it the Giant Impact. A protoplanet named Theia, the size of Mars, was on a terrifying collision course with early Earth. The impact was devastating. Theia sheared Earth to its core, Material from the Earth's mantle, as well as what remained of Theia, was ejected into orbit. The debris from that impact, the dust, the rocks, and the molten magma from the core of the Earth, went on to become the rocky satellite we call the Moon. As violent and terrifying as that collision was, it also controlled our destiny. For without it, there would be no moon, and life on Earth, evolution itself, would not have been possible. Elsewhere in space, there are meetings so huge they seem like science fiction. They are spectacular collisions within tightly packed star clusters. It is believed they happen when older, smaller stars are drawn together by gravity. They orbit closer and closer. Sometimes a smaller one will actually plow right through a larger one. In galaxies across the universe, this solar dance plays out on a scale that's unimaginable, with sun-like stars hurling toward one another at remarkable speeds. They meet in spectacular displays. A massive collision of light and gas and debris. The result? A star that's more blue than most stars in the cluster. They are called blue stragglers. But several stars coming together in space is not the largest collision the universe has to offer. The Hubble telescope has recently discovered two star clusters that are in the process of colliding in the massive star-forming region known as 30 Doradus, or the Tarantula Nebula, more than 170,000 light-years away. Gravitational forces are drawing these star clusters closer and closer to each other, into a dense, extraordinarily bright and gaseous region. Astronomers believe they are witnessing a strange and powerful force in the universe, and the creation of a luminous new neighborhood inside the tarantula. And when any new neighborhood is formed, not everyone sticks around. Scientists have discovered what they believe is a runaway star from that massive merging inside the Doradus Nebula. Most stars, like our Sun, move in proper motion, but not this one. Scientists believe at least one runaway star was ejected during an interstellar collision. The star they have their eye on is a gigantic body, 90 times heavier than our own Sun, and traveling at more than 250,000 miles an hour. It is believed that this homeless runaway star has already traveled 375 light-years from its stellar nursery home. A real shooting star, if ever there was one. Next, we'll see a collision that came dangerously close to Earth, relatively speaking, just 20 years ago. And cameras were there in space to capture every breathtaking moment. On March 24, 1993, astronomers Carolyn and Eugene Shoemaker, along with David Levy, were in a California observatory when they discovered a fragmented comet orbiting Jupiter. NASA trained the Hubble telescope on Jupiter, and the Galileo spacecraft was already on its way to observe this rare event. This would be the first time we would be able to watch an impact on a planet that was not our Earth. Further observations revealed that the comet, now named Shoemaker-Levy, was once a massive comet that had been trapped by the giant planet's gravity. It began to break up after a recent close pass. That 700,000-mile train of comet rubble was expected to return and collide with Jupiter in July the following year. In early July of 1994, a meteor shower began to rain down on Jupiter. One by one, the larger fragments of Shoemaker-Levy, mountainous boulders, blasted through Jupiter's atmosphere at 134,000 miles per hour. Some vaporized instantly, but the more massive comets drawn by Jupiter's powerful gravitational pull created giant fireballs and shock waves that rippled across the planet. They ripped a hole in the planet's atmosphere that was larger than Earth. Scars from the impacts were more visible than the Great Red Spot. They lasted for months. It was the first direct observation of an extraterrestrial collision in our solar system. And a violent demonstration of the force of Jupiter's gravity. The largest planet in our solar system, Jupiter has more than 60 moons circling around it. Its 4 largest were first observed by the astronomer Galileo more than 400 years ago. But the planet also has dozens of smaller, irregularly shaped moons. Asteroids or comets, really, that were caught by Jupiter's strong gravity and taken into orbit. The planet simply collects objects in space. The largest planets orbiting our sun can be found in the far reaches of our solar system. They are the gas giants, like Saturn, Uranus, and Neptune. Jupiter is one too, And it may look as solid as rock from space, but the planet is made mostly of hydrogen and helium, along with some ammonia and methane. It is a massive planet, but made almost entirely of gas. Standing on the surface would be impossible. You'd simply sink right through until you were crushed by the intense pressure, much like going to the bottom of the ocean without a submarine. But if you could stand on Jupiter, you'd immediately experience the planet's powerful gravity, 2.5 times stronger than on Earth. Let's take a healthy 200-pound astronaut and let him experience Jupiter's gravity. He may weigh 200 pounds back on Earth, but on Jupiter, he'd weigh 480 pounds. Now let's put our astronaut onto the surface of Pluto, which has just 1/15 the gravity of Earth. This same 200-pound astronaut would weigh just 14 pounds on Pluto. Floating above Earth, it may seem there's no gravity in space, but there's really no such thing as zero gravity. In fact, gravity is everywhere in the universe. Gravity is what keeps the planets orbiting around the sun. It also keeps matter from coming apart. Without gravity, everything would cease to exist. But there are such places in the universe, mysterious places, where gravity and the laws of physics break down completely. That's what would happen if we were to travel too close to a black hole, as we'll see when we come back. Black holes began to form not long after the Big Bang. They occur when a massive star collapses in upon itself, causing a supernova. Try to imagine an explosion of such extraordinary size and magnitude occurring in virtual silence. Without air to carry the sound, the quiet found in space tempers the power and otherworldly beauty of the birth of a black hole. Unlike sound, light travels through empty space as a wave, carrying electromagnetic energy in it. But there are some places in space where the forces are so potent, stars can be compressed and swallowed. In black holes, the forces of gravity are so strong, not even light can escape. Imagine an ocean liner drifting through space. The movement of stars and black holes produce gravitational waves that draw matter inward toward a deadly, inescapable whirlpool of energy. Get too close to a black hole, and the gravity becomes too strong to overcome, even for masses as large as stars. To escape that kind of gravity, you would need a speed greater than light. In other words, there is no escape. Our ocean liner wouldn't stand a chance. NASA has already begun to explore the universe with satellites and space-based telescopes that search for massive black holes and other astronomical phenomena. But what might it be like if one day we could mount an expedition to see firsthand one of these cosmic mysteries up close? Scientists have discovered many black holes in the Milky Way. If they are big enough, they can capture nearby stars, planets, and even smaller black holes. How many there are, no one really knows. Perhaps billions. Any future explorers hoping to get a closer look at a black hole will have to keep their distance. Otherwise, the extreme gravity will act like a giant invisible hand, reaching out and pulling them in, bringing a fatal end to their voyage. Once a spaceship or a planet reaches what's known as the event horizon, there is no turning back. In smaller black holes, forces of gravity are stronger toward the center. As objects draw closer to the event horizon, they would be stretched into long, thin shapes. Their matter would then be ripped apart. Here's how it works. Suppose NASA launched 3 exploratory probes to study a black hole. They would be able to record data and send it back right up until they reach the event horizon. At that point, the probes would undergo what scientists call spaghettification. It would occur in the microsecond before they were obliterated. Here at the event horizon, light bends and photons are trapped forever. It's a place from where nothing can return, and all known laws of physics cease to exist. Not even the forces or the light from an exploding star could escape. Neither man nor machine would be able to relay back what happens next. If we were able to take one last look at our universe, how long might it be before everything we knew seemed to shrink away into darkness? Deep inside this prison is said to be a place where photons pool, where hellish temperatures can reach 20 million degrees and neutrons melt. If only some of the light could be reflected back, what would we see? Einstein's theory of general relativity allowed for a space-time curvature to connect 2 distant locations through a theoretical tunnel known as a wormhole, a shortcut through space-time. Could it be possible that wormholes are the bridges and doorways between different places in our universe? Could they one day be used for travel, like a tunnel through a mountain? The forces in our universe are extreme. When we come back, we'll show you a preview of how the universe ends. Don't worry, we won't be around to see it for ourselves. Launched in 1990, the Hubble Space Telescope orbits the Earth, and for decades, it's been beaming back images that are helping scientists unravel some of the great mysteries of the cosmos. Inside Hubble are multiple cameras. Some of these cameras are so light-sensitive that they would be destroyed by taking a picture of a star that's visible to the naked eye. These are the cameras used to peer deep into space at the faintest stars imaginable. The oldest light to arrive at the Earth. Beginning in 1995, Hubble began to capture deep field images in space, revealing thousands of galaxies. By peering so far into the distance, Hubble was also peering far, far into the past. It's a past that can actually tell us a lot about our future. The universe may have begun with a Big Bang, but there are several scientific theories predicting its demise. Will it all end in a big chill, a big rip, or a swirling mass that condenses into a big crunch? Let's start with the most peaceful theory, so we can get used to the idea of everything in the universe finally coming to an end. Then we can work our way up to the sheer terror scenarios. One theory has the universe expanding forever, with galaxies drifting further and further apart from each other. This is known as the Big Chill theory. Over time, long stretches of time, stars would begin to lose their energy. They would die out, one by one, the sky turning darker and darker. The universe would continue to expand, slowly but never stopping, until it would become a very cold and dark place. Earth would suffer the same fate. The light and heat it receives from the sun would, over time, diminish. Our magnificent sun will eventually use up all of its hydrogen and expand into a red giant before burning itself out. Eventually, the universe, like Earth, would end in what scientists call the Big Chill. For reasons unknown, since the Big Bang, the universe has been expanding at a faster and faster rate. Astronomers attribute this continual expansion to the presence of dark energy. We don't know much about it yet, but scientists believe that 70% of the universe is comprised of dark energy. Einstein was the first to realize that empty space has properties, and he predicted that empty space can also have its own energy. This brings us to our second universe-ending scenario. If you thought the Big Chill was bad, you may want to close your eyes for this one. As more and more space is created, there becomes more and more dark energy, causing the universe to expand faster and faster until gravity is completely undone. Under this scenario, known as the Big Rip Theory, galaxies would separate. Molecules and atoms would be torn apart by the speed of this furious expansion. And eventually, stars and planets, everything, would be ripped to shreds in a universe that would no longer have any gravity or structure, all because of the mysterious dark energy, a theoretical cancer of space. The Big Bang might have been explosive, but the Big Rip would be even more violent. There is a bright side, however. Physicists who believe in the theory predict that the Big Rip won't happen for another 22 billion years. The final end-of-days scenario in our universe death spiral might be called coming together, but not in a good way. Imagine all the stars, planets, every nebula and galaxy being pulled back to a point in the center of the universe. Our inflating balloon has begun to deflate. And everything in the universe begins to crash back together toward one center, a supermassive black hole. This scenario is known as the Big Crunch, and you can probably see where this is going. It's the Big Bang in reverse. Over 10 or 20 billion years, where all matter collapses into an infinitely dense area of zero volume, a singularity. And then maybe, just maybe, we do it all over again.